it is not here, omega minus mass 1670 MeV and strangeness minus 3. So, if it has to decay into strong interaction, the only possibility perhaps is cascade and K, I think, cascade and K bar. The cascade has strangeness minus 2 and this is minus 1 because this is strangeness minus 3. Since strangeness has to be conserved in strong interaction, it can decay only into cascade and K bar, but look at their masses. Cascade mass is 1320 MeV, K bar is almost 500, 490. $1810 MeV is needed, whereas this guy has got only 1670 MeV, so it cannot decay. So it decays by weak interactions, exactly like lambda, sigma, cascade, with a lifetime of around. That's what I mentioned on the very first day, 10 power minus typical weak interaction lifetime. So this you will regard as a particle, and now we are putting cascade minus and the sigma 1385 and cascade star 1520 and delta 1236 into one SU3 multiplet. These are all the resonances, whereas this is a particle. So you can see that particle and the resonances have to be clubbed together in order to understand strong interaction physics. This is a better example, because this decays only by weak interactions, whereas these guys decay by strong interactions, and so manifest themselves only as resonances. Any other question? So no other question? You can ask any question, don't be shy. I'm addressing students because every question will be treated with respect. No question is a stupid question, only answer sometimes can be stupid, but all questions are relevant. So ask any question, even an elementary question. Don't be afraid of asking any question. I hope you are following what I am saying. So far what I have said is rather elementary, I would think, but still if I have not done it properly, you can always ask. I can even repeat some part. If you think that some portion was not clear, I can even repeat.
Sir,
Yeah.
Is there any experiment such as Stern-Gerlach for isospin property?
See, Stern-Gerlach was an important experiment which established the angular momentum quantization and in some sense established the spin half nature of electron also. There is no such analogy. Do not go into that much detail about isospin. Isospin is used only to classify symmetries, classify the particles, and one should not ask for anything more from it, I would say, because now we know that it is not of fundamental significance, whereas the spin of the electron is of fundamental significance. Okay, and proton is ordinary spin also, it has magnetic moment. That is even more important than the isospin property of proton. Isospin property of proton is historically very important. That is how we discovered the quarks and everything. But in my opinion, it is not of fundamental significance. You cannot go any further than just this isospin property, namely I and I3. See, you can what about SU3? SU3 does it have any dynamical thing like magnetic moment or Stern-Gerlach experiment? There is no such thing. SU2 is only a step. SU3 includes SU2, remember. All SU3 multiplets will be isospin multiplets also, but SU3 puts together different isospin multiplets into one bigger multiplet like octet or decimal. So, these are all classification, they are nowadays called classification symmetries, no dynamical significance at all. The dynamical significance is coming to some symmetries in the standard model. On the first lecture, I talked about standard model. I said electroweak electroweak part of the standard model is based around the Lie group SU2 cross U1. That SU2 is of fundamental significance. You will see that SU2 is very similar to this classification SU2. Nowadays, this is called classification SU2, and that is the fundamental gauge symmetry SU2 cross U1 cross SU3. There also there is an SU3. That SU3 should not be confused with this SU3. I am going to introduce that SU3 soon. Mathematically, both are SU3, but this SU3 which I am talking about now is only of classification significance, whereas the SU3 which comes in the standard model is of more fundamental significance. I will introduce it if not today. I might start introducing it even today, and we will develop it further. Whole of quantum chromodynamics is based on that SU3. So, we have to see which is more important, which is more basic and which is less basic. That way SU2 and SU3 which I am talking about, we will soon outgrow this and go into into the standard model. Then you will see that this SU2, SU3 are very important, because it is this SU2 and SU3 which helped us to discover quarks. Quarks are not discovered yet, I am only introducing it. How they were discovered also we are going to talk about. How experimentally the existence of quarks was confirmed, all that I am going to talk about. But all that would not have come without this SU2, Heisenberg's SU2 and Sakata's SU3. Okay? Yeah, go ahead.
So I think Sar is asking another question.
Yeah.
Is there a simple example of accidental symmetry?
Accidental symmetry.
Is there a simple example of accidental symmetry?
Axial. Accidental. SU2 and SU3 are accidental symmetries.
Is asking, is there any simple example? Is there any simple example of accidental symmetry?
Well, these are the examples. I cannot think of anything more simple. Why they happen to be symmetries, I can explain only after I develop the cork model a little bit more. I can give you the reason straight away. See, it turns out that the SU3 symmetry is because SU3 symmetry is a symmetry because the three quarks U, D, S are all very small in mass and similar to each other compared to 1000 MeV for nucleon and more than 1000 for all the other hadrons. The masses of these three quarks are very small. You can even put them 0. If you put them 0, you get SU3, exact SU3. You don't put 0, it's some small number. So, it just happens to have that number U, D, I will discuss the masses of the quarks a little later, but you will see that the masses of the quarks U, D and S are so similar, so there is a symmetry. In the same way, the masses of the U and D are almost similar, like proton neutron mass are similar, the UD quark masses also are similar, and that is the reason, because in the Lagrangian mass also will come, and hence there is a symmetry. They behave alike because they are almost identical mass. You might say that is the reason. For baryon number also is an accidental symmetry, but that explanation is a little harder. In the standard model, as constituted now, the particle content of the standard model, which we will come to later, you find does not allow a baryon number violating interaction. That is all. But as soon as you go to a bigger theory like supersymmetric version of the standard model or grand unified model, then other fields come in, then you can violate baryon number very easily.
Sir, I have one basic question, sir.
Yeah.
So what is mean by gauge symmetry? In a simple sense.
Yeah.
What is my gauge symmetry?
Gauge symmetry, all of you know, because in electromagnetism, although electric and magnetic fields are there, for many purposes it turns out that you have to introduce the potentials, scalar potential phi, and electric field is minus gradient of phi, and vector potential A vector, and magnetic field is curl of vector potential. Actually, in that case, the electric field also has to be changed, E equal to minus grad phi minus I think 1 over C dA by dt. Remember? So the electric and magnetic fields are space or time derivatives of the potentials. Relativistically, it is a 4 vector potential. Phi you can call A0, the 0th component of a 4 vector potential, and the spatial components of the 3-dimensional vector. And there is a thing called gauge transformation. Although the potentials are useful, you will find that the potentials don't the potentials are ambiguous. You can change the potentials. A mu can be changed to d mu of another ordinary function. You know that curl of A you write as magnetic field. You add to A gradient of any function, arbitrary function. Still the magnetic field will not change. That is called gauge invariance. Similarly, for electric field is very simple. You say potential, you add a constant to potential, the electric field will not change. So electric field or magnetic field or the physical quantities, you might say, they do not change when you change the potentials. Although you use potentials, why do you use? Because in dynamics it is potentials which come. I think I already mentioned yesterday that in the Lagrangian and the Hamiltonian potentials come. Another very important reason, you try to write down the quantum mechanics or the Schrodinger equation for a particle in electromagnetic field, you cannot write it down in terms of the field. It is the potentials which come, P minus Ea by C, remember, vector potentials come, and it is a scalar potential which will get added. So without potential there is no Schrodinger equation, no quantum mechanics. So in higher forms of mechanics, especially in quantum mechanics, potentials are important, so we are forced to introduce it. But unfortunately potentials are not unique. If you make a gauge transformation on the potential, the fields remain invariant, the theory is invariant. That is called gauge invariance. That is a gauge invariance of electromagnetism, and that concept gets generalized in Yang-Mills theory to a very large extent. Yeah, sorry.
So what is the physical consequence of this gauge term, sir? Because anyway only electrical and magnetical are real.
Yeah, but you potential, why do you use potential then? Even ordinary electrostatic potential you use all the time, it is very convenient.
Yes, sir.
That is why it is a matter, originally it was introduced as a matter of convenience, for mathematical convenience, but now we know it is very important, because without potential I cannot write down Schrodinger equation. Can you write down Schrodinger equation in terms of the electric field? In Schrodinger equation, minus del squared over 2m, h cross squared del squared over 2m, kinetic energy operator, plus potential. Without potential there is no quantum mechanics.
Yes, but by adding some other constant term, what gain that we obtain?
No. So there is an invariance in the theory, there is a symmetry. See, symmetries are going to play a very important role in all of particle physics. One of the symmetries is you change the potentials, still the theory remains the same, it is invariance. That is called symmetry. Many times it is convenient to change it without changing the physical content of the theory, and we have to recognize if there is a symmetry, we had better, I mean, we are not inventing that symmetry. Ordinary Maxwell's electromagnetic theory coupled to charged particles has that symmetry. Okay?
Yes, sir. Please, you can start, sir. I think you are.
So now maybe we can start. Okay? So let me continue the cork model of the hadrons. So I have to compose all the baryons and mesons using these 3 quarks. Baryon, as I already said, is made up of 3 quarks, and the decimate baryons I will call B star. That also is 3 quarks, because that is also baryon number 1 object. And meson I will indicate by Bm, which is a quark and an antiquark. So I will illustrate this with more details. Baryons, proton is made up of UUD. You can see the charge is balanced, 2/3, 2/3, minus 1/3 proton charges. 1. Neutron will be 2 Ds and 1 U. Lambda will be UD. Stein cork has to be there to get Stein is -1. They are all additive quantum numbers. But this is not exactly the correct way of writing it, because this UD part has to be antisymmetrized. First particle can be U, second particle can be D, that is the notation. Or first particle can be D, second particle can be U. Remember, these have to be understood not only as a composite object, but as a wave function. Multiplying the 3 wave functions of the constituent particles, you get the wave function of the bound state proton. Here UD minus DU into S. Okay. Why do I do this with a minus sign? You must be able to guess. In angular momentum theory, you would have learned when you add 2 spin half particles like 2 electrons, you can have either spin 0 or spin 1. And spin 0 is obtained by adding spin up, spin down minus spin down, spin up divided by root 2 just to normalize. That antisymmetric thing only is spin 0. So I have antisymmetrized it because isospin is 0 here. I3 and I3 and S, everything you can balance, but I, how do you get? To get it, you have to put this antisymmetric combination, then only I equal to 0. Sigma plus UUS, sigma minus DDS, sigma 0. Sigma 0, as far as the additive quantum numbers are concerned, I mean all these are additive quantum numbers except for I. I is a vector quantity, so vector addition. The addition of angular momenta, coupling of angular momenta theory, you have to bring it to your mind. Angular momentum theory in quantum mechanics. How, when you add 2 angular momenta J1 and J2, what are the total angular momentum? Total angular momentum can be either J1 minus J2 if J1 is larger, and then go on increasing in 1 unit up to J1 plus J2. So spin half plus spin half, either 0 or 1. Spin 1 plus spin 1, you will have 0, 1 and 2. All those rules of adding angular momentum have to be used for isospin addition also, because as I said, the mathematics of isospin, not physics, mathematics of isospin is identical to the mathematics of angular momentum. Sigma 0 is also therefore UDS if you think of the additive quantum numbers, but that has to be amplified to UD plus DU into S. The symmetry combination only gives you isospin 1, and let me just mention it. In the case of angular momentum theory, angular momentum addition, half plus half, become too small, angular momentum addition of angular momentum, spin half plus spin half, let me indicate like this, is either 0 or 1. So this 0, the spin half wave function can be written as either alpha or beta. Alpha is spin up, namely spin plus half minus half. These are the two ways, two components of this half, And so now we are considering the two particle wave function. Two particle wave function can be alpha, first particle 1, second particle also alpha, in which or first particle alpha, second particle beta, and plus beta alpha. Since there are two terms, I have to divide by root 2, and beta beta. So all these together corresponds to this 1, and this is the magnetic quantum number plus 1, magnetic quantum number 0 or minus 1, and this is the triplet wave function corresponding to total spin 1. And then there is a antisymmetric singlet, which is alpha beta minus beta alpha divided by root 2. Okay. So all these I equal to 1, and this is I3 equal to 0, and I also is 0. I equal to 0 means I3 also 0. So there are two wave functions here, two wave functions here. When you multiply, there are 4 wave functions. One becomes I equal to 1 triplet. I equal to 1 triplet is symmetrical. When you interchange, for all of them they are symmetric. I equal to 0 is antisymmetry. So exact analogy, the symmetry combination gives you, because this is isospin 1, whereas this is isospin 0. Cascade 0 will strangeness minus 2, so it should have 2 strange quarks. Cascade minus is D SS. So that is the octet. The complete octet baryon quark composition is given here. So mesons. Is it visible? I can use this part. Yeah, I think you can use it. Again, the octet of mesons, pi plus d bar u. Remember, d bar will have charge plus 1/3, and u is plus 2/3, so plus 1 comes. Pi minus the antiparticles, so antiparticles of this has to come. So d and u bar. Pi 0. Here again, pi 0 can come from uu and or dd, but if you look at it, u bar u minus d bar d divided by root 2 I will write. This is an isospin triplet. We are adding again isospin half to isospin half to give you isospin 1. So by my argument, just as we did here, I should have put plus. Why I put minus? It is an important question which I will completely clarify only maybe tomorrow, I mean next week, but I will mention the reason now. It turns out, so this has to be clarified by further, we will do it later. U and D is an isodoublet. And if you take antiparticles, first of all, you cannot write u bar d bar, you have to write d bar u bar, because the convention is to write the I3, the higher I3 above. So d has I3 equal to minus half, d bar has I3 equal to plus half, so that has to go to the top. But it turns out that this is not enough, you have to put a relative minus sign, then only it has the correct transformation property, which I will prove later. Is also an isodoublet. It requires a little bit of mathematics of isospin SU3, so to be proved, let us say. People who already know that mathematics may be able to prove it as a homework, but I will do it in any way. So that is why, because of the relative minus sign instead of plus, when both of them are particles, one of them is antiparticle, remember there is always a relative minus sign. Next I have to write eta. Eta by the same token I equal to 0, so I equal to 0 part has the plus 1 now. But it turns out that this is not enough, because S bar S also has all the properties as far as quantum numbers are concerned, you have to add that. So some alpha times beta, alpha and beta will be determined. This is, remember, in SU3 this is a member of an octet. There is an SU3 singlet also, I have not talked about, that is called eta prime, and that SU3 singlet is actually eta prime. And since it is a singlet, everything comes with equal coefficients. Now 3 terms are there, so I have to put 1 over root 3. And this has to be orthogonal to this, because this wave function is a different quantum state. So it has to be orthogonal to this. Orthogonality of eta and eta prime fixes alpha to be 1 over root 3. So an additional 1 over root 3 we have to multiply, and this is minus root of 2/3. You can verify that now this is orthogonal to this. So that is a complete representation for eta. But anyway, that is a matter of detail, we can forget it for the moment. Since this is an octet, remember, it's not only isospin properties have to be balanced, but SU3 properties also have to be balanced. And this is a member of an octet, whereas there is a singlet meson which is called eta parameters. This is I think 550 MeV, this is much higher, I think more like 900 MeV. I had not talked about it earlier. But let us talk about the strange particles. K plus will be S bar u, as you can verify, whereas K minus, K0, that is the doublet. So it will be S bar d. Now the antiparticles, K minus will be u bar s, and K0 bar will be d bar s. You can raise the question, see, K plus and K minus have different charges, so they are different particles. What is the difference between K0 and K0 bar? Just think a little bit. K0 has strangeness minus plus 1, whereas K0 bar has strangeness minus 1. So this K0 bar mixture is very important. I will talk about it later. It's an important thing. So this has to be proved later. Okay. So any question? If there is any question, I will answer it now. Before I will rub it off now. Okay. Shall I rub it off? I think I have started writing small letters. I should go back to big letters. This quark properties table is very simple to remember. Please remember it and try to balance all the quantum numbers when you write down a quark composition for any barium. So let us go to B star now, the decimate. That is also made of 3 quarks. The decimate and spin parity is 3 of pair. Let us start with the delta plus plus. Three U's, 2/3, 2/3, 2/3, so total charge is 2. Delta plus U D, then additive quantum numbers will balance, but we have to do something more to this now. That to explain that, I have to go to a little bit more detail about the SU3 representations. This tenfold representation is supposed to be a symmetric representation of the 3 quarks, and for that you have to use the language of permutation symmetry. I do not know how many of you have learnt permutation symmetry. The concept of Young's tableau. Little bit of group theory of the permutation symmetry is useful here. I will not use too much of it. Young's tableau. each square represents one quark. We have 3 quarks, so I have multiplied. You can call them as wave functions. Okay, so actually they correspond to this is a threefold representation of SU3, 3 into 3 into 3. And again, remember these are wave functions. So there are 3 wave functions, 3 wave functions, 3 wave functions. So total 27 wave functions are there, I suppose. So they are resolved into again the various representations which we have already introduced, but a little bit more mathematics of this I will do it later. But for the moment I want only one property, so I am taking that. Tenfold comes because from 3 quarks we can form the tenfold representation. Then there is 8. Actually, it turns out there are 2 8s, and then there is a singlet. So 10 plus 8 plus 8 plus 1 is 27. You can verify. Now, from the point of view of Young's tableau, it turns out that this is represented by this row of 3. The meaning of Young's tableau is very simple. Anything in a row are symmetric, so it is a completely symmetric wave function of the 3 quarks. Whereas this is a completely antisymmetric, which is represented as a row, as a column. Whereas these are mixed symmetries, symmetric between these two and antisymmetric between these two. There are 2 mixed symmetries. So that is the Young's tableau representation of the 3 quark wave function. So because of that, you can see that the wave functions have to be symmetric. This is already symmetric. So this has to be symmetrized. That is all the point I want to maintain. Symmetric. And so I have to rewrite it more elaborately, like 1 over root 3. First particle is u, second particle also u, third particle is d, and then symmetrize them. U1, D2, U3 plus D1, U2, U3. This is somewhat cumbersome to write, so I will simplify it to writing. Simply, my notation is this represents the first particle, this represents the second particle, this represents the third particle. Not here, but here. And here it is U, D, U, and that is D. It is somewhat simpler to write, but meaning is this is first particle, second particle, third particle, third particle. So that is delta plus. Delta 0 is d du. There again I will use this notation, 1 over root 3 d du plus dud plus udd. Whereas delta minus is simple, just 3 d's, minus 1/3, minus 1/3, minus 1/3 gives you minus. Now let us go to the sigma. This is not the usual the octet sigma which we have got. To distinguish it here, since I am not going to write the mass, we call it sigma star, the excited set of sigma, the spin parity 3/2 object. By counting the strangeness, you can see that it has to be UUS, but we have to symmetrize. Sigma star. First of all, there is a symmetrization involved for isospin purpose because the isospin 1, so it is UD plus DU and then multiplied by S. But then the symmetrization needed for SU3 to get the correct SU3 characteristic, we have to symmetrize all the 3. So that will make it to 1 over root 2 into 1 over root 3, it will become 1 over root 6. UDS. I mean there are 6 terms here because 3 particles have to be permuted, 3 factorial. DUS, USD plus DSU plus SUD plus SDU, is it? SDU, I think. Okay. That is sigma star and sigma minus, sigma star minus. Simply written it is DDS, but to the symmetric characteristics dictate that it has to be one over, it is exactly like this. DDS DSD plus SDD, then cascade star 0 charge 0, it is 2 strangeness 2, so 2 strange quarks. So this will again become 1 over root 3 U S S S U S plus SSU. This I will not write down, you have to replace U by D. Replace U above by D. It's very easy to write down. It's exactly like this, except that wherever U comes, put D. Then what is missing? Omega minus. Omega minus is very simple, but it is simply 3 S quarks. Omega minus and delta plus plus and delta minus. This is 3 U quarks, this is 3 D quarks, and this is 3 S quarks. So that's all. That is the quark composition of the 3/2 plus decimate baryons. Now I want to go to the next step in the historical process. As I said, I am following the historical path. This I will keep for the time being to remind me that I have to do something, which I may do only next week, it looks like. Next step is to realize, it turns out that there is an empirical fact, it turns out that the quark interactions by and large not only are SU3 symmetric, but they do not depend on the spin of the quark, whether the spin is up or down. So the symmetry is even bigger than SU3, that is called SU6 symmetry. If you look at the the wave functions of the quark, let us call them psi I, you have U, this is now when I say arrow up, it is that what I called alpha, the spin up, ordinary spin, this is just the ordinary spin, and spin down D S up, S down. So there are 6 objects of which, so when you make a unitary, see SU3 itself, I am going to talk about it in detail later. Remember SU3 is a symmetry of unitary transformations on 3 objects UDS, but it turns out that there is a symmetry, a 6-dimensional unitary transformation on this. So that is called SU6, I goes over 1 to 6. So you can classify the hadrons according to SU6, that brings even more collapse, even more simplicity into the so physical meaning is forces are spin independent. Or approximately, these are all approximate symmetries. It is even more badly broken than SU3, which is badly broken as compared to SU2. The higher symmetries are more and more badly broken, but still they are important in understanding the classification. Forces are approximately spin independent. Whether it is spin up or spin down, the forces are the same, approximately same. So it is a bigger symmetry. This was actually discovered around 1965 by Giurse, Radicati, and Sakata. same Sakata, not Sakata, this is Sakita, I am sorry. And Sakita, it's a different Japanese species, Sakita. So, under SU6 we have to classify the particles. We have classified the particles first with isospin, then with SU3 like either octet or decimet. But now I am going to talk about the multiplet of SU6. We have to think of a 56 dimensional multiplet, and that can be decomposed into an octet with the spin half. So, it will be a 2 representation under ordinary spin rotation. This is in SU3 rotation. As far as SU3 rotation is concerned, 8-2 plus the decimet spin 3/2. So, it is a 4-4 representation for ordinary spin, and this is a 10 plus yeah, that is all I think. This is the B, our B, this is our B star. How many particles are there? 8 into 2 16 and 10 into 4 40, together 56. So, under SU3 cross SU2, this is the decomposition. This is the internal symmetry, and this is ordinary spin, the same spin which started with all of the electron spin, like electron spin. So, we are combining dynamical, this is called a dynamical symmetry, because now the real dynamical spin also is included. So, this 56 will correspond to different total spin objects. So, so it will combine spin half and spin 3/2, B and B star into one multiplet. That is what we have done here. Now, again SU6 is not even as important as SU3. I mean, SU6 is not even that important, but in the historical process it played a very important role for the following reasons. That is what led to the discovery of the new quantum number called color. So, I am going to describe that now.
Your font size has grown very small.
Yeah, unfortunately. So, I will. So, I don't know what I should do. Can't he magnify it further? I don't know whether Kripa can magnify this. இதை கொஞ்சம் மேக்னிஃபை பண்ண முடியுமா இன்னும்? ட்ரை பண்ணுங்க. Now, I will remember that I should not do this, but so what I am going to talk about is this delta plus plus wave function. Look at the delta plus plus wave function. The discovery or invention of color, the color quantum number. By color here we do not mean blue, red, red, blue, green, etc., not the optical color, but it is just a name introduced. Again, it is Gell-Mann who invented all these names and they have stuck. Gell-Mann was very good in inventing names like quarks, then color, quantum chromodynamics, first strangeness. All these names were invented by Cork and they become standard practice now. So, let me write down the wave function of this object. By this I mean the wave function of delta plus plus in one particular the third component of the spin m equal to plus 3/2. Remember, it is spin, ordinary spin 3/2. So, m quantum number can be plus 3/2, plus half, minus half, plus 3/2, plus half, minus half, minus 3/2. But I am taking plus 3/2. So, how will we write down the wave function? First of all, the quark composition, 3 quark wave function, and then the spin wave function I will indicate like this. You know how to form the total spin m quantum number 3/2. Of course, the total angular momentum also has to be 3/2, but the third component m is actually the J3. Remember, the magnetic quantum number so called is plus 3/2 is obtained by putting plus half, plus half, plus half together, then all pointing in the same direction, giving you plus 3/2. Then the spatial wave function, I will call it psi, which is a function of the 3 spatial coordinates. So, this is a complete quark wave function, the 3 quark wave function composing the delta plus plus object. Now, let me just make the statement: relative orbital angular momentum of any all these 3 objects is 0, and so the total angular momentum also is 0, because the total angular momentum of this object is 3/2, but that comes from spins alone. Orbital part is 0. So, that is the characteristic of any ground state. Ground state orbital angular, like in hydrogen atom, you can see ground state wave function is orbital angular momentum 0, the S state. So, same thing is presumably valid for the quark bound state also. Now, delta plus plus is not the ground state of the hadrons, it is proton, which is the proton and neutron, which are the ground states of hadron. But now remember, that is where the SU6 comes. SU6 puts the proton, neutron and delta plus plus in the same multiplet. So, the spatial wave function has to be the same, and hence this also is, as far as spatial wave function is concerned, is a ground state. So, total angular momentum is 0, that means psi is symmetrical. If you interchange R1, R2, R3, it is symmetrical, spatial wave function is symmetrical. What about the other parts? This is obviously symmetric, this is also obviously symmetric. So, the total wave function is symmetric under interchange of SU3. SU3 is U, D, S, etc., and this is symmetric. Spin and space now. But this is a catastrophe, because delta plus plus is, since total angular momentum is 3/2, according to one of the ground rules of quantum field theory, so called spin statistics theorem, which can be proved in quantum field theory, any half integral spin object has to have Fermi-Dirac statistics, namely the wave function has to be, no, that is not the correct way, I am sorry, let us not put it that way. We are talking about the 3 quark wave function. Each quark is a spin half particle. So, it has to satisfy the 3 quark wave function has to be antisymmetric under the complete interchange. Since it is a 3 quark wave function, it has to be it is a quark wave function. The quark, when you interchange the properties of the quarks, it has to be antisymmetric. That is, even in atomic physics you would have encountered it. The multi-electron atoms, the wave functions have to be antisymmetric. Only because it is antisymmetric, Pauli principle is there. Pauli principle is only a side consequence of antisymmetry. Antisymmetry is the more fundamental consequence, fundamental property, and Pauli principle can be derived. If it is an antisymmetric thing, if you put 2 particles in the same state, it is 0. So, Pauli exclusion principle automatically is built into antisymmetry. Antisymmetry is the more general principle, of which Pauli principle is a consequence. That is the way to correctly understand. So, antisymmetry, whereas for Bose particle it is symmetric. That is, that is needed. It was Bose who realized it first in the context of photons. Of course, he discovered it before quantum mechanics was discovered, but he had to count all the particles when you interchange as one state, when you interchange the 2 things as one state. That itself does not completely give you symmetry, it can give you symmetry or antisymmetry. Now we know that it is symmetry. So, that is the Bose-Einstein statistics for integral spin particles like photons, and for half integral particles like electrons or quarks. Quarks we have still not completely introduced into physics, but if it has to be introduced at spin half, it has to be spin half, otherwise you cannot understand the baryon spin as half, because 3 quarks give you spin half baryon only if each quark itself is a half integral spin. The simplest half integral object is spin half. So, it violates Fermi-Dirac statistics, which has to be one of the fundamental principles of quantum field theory, violates Fermi-Dirac statistics. How do we solve it? Puzzle solved. By bringing in another quantum number. an extra quantum number called color, which can take 3 values 1, 2, 3. I mean, Gell-Mann originally called it, I think, red, green and white, maybe the American flag or something like that, but let us simply call it 1, 2, 3, although it is called color, another quantum number. Then the wave function is therefore now amended into, put one more wave function, color wave function. In terms of color, let us call the color, I am going to call it simply 1, 2, 3. This is the color wave function, chi color, and this is antisymmetry. So the total wave function is antisymmetric when you interchange not only these 3 and color. So that Fermi-Dirac statistics is satisfied. That is the solution. That is the invention of color, which plays a very important role now. See how it entered. It entered through the back door in some way, not through back door, because Fermi-Dirac statistics has to be simplified. If cork model is correct, Fermi-Dirac statistics has to be satisfied. Meanwhile, there are other suggestions for quarks. Since quarks were peculiar objects, they thought it satisfies parastatistics and so on. That was Greenberg's suggestion. But finally, what won is simply that they are not satisfying parastatistics, it satisfies only Fermi-Dirac statistics, but we have to have an extra quantum number called color. That is the discovery of color quantum number, which as we know is very important, because from this only came. So now we can forget about these things. What is important is color. Once we have got color, we make a gauge theory, SU3 gauge theory, SU3, but in color now, not in the Gell-Mann name on SU3. So we indicate it by putting this, but mathematics is the same, and make it into a gauged color symmetry, gauged SU3 color, and that is quantum chromodynamics. Quantum chromodynamics. Why quantum chromodynamics came is another story. I think I will not go over that today, maybe next week. Quantum chromodynamics surface. So that is the other part of standard model. Yeah.
Sir, I think could you increase your font size, sir? I think now it is
Again becoming small, huh?
Font size.
I
think it becomes small.
So I don't know how to cure this defect of mine.
No problem, sir. Just hereafter, if you are further.
Yeah, hereafter I will increase it again. I mean, you tell me again and again, I will go on correcting myself. Okay. I think I can prove this now. Before proving it, I will do a little bit of mathematics. Yeah, there are still almost 40 minutes are there. So 35 minutes at least. So that is enough for doing what I want to do. I don't know whether I will be able to prove it, but at least I will introduce the mathematics of SU2 and SU3. I have been talking about SU2 and SU3 symmetries, but what they are mathematically. So let me talk about that. Mathematics of SU2 and SU3, and you can easily generalize it once you understand these two. So they are called Lie groups. These are called Lie groups. First, let me talk about SU2. Either UD you can take, or proton and neutron. So let us take UD, since we already introduced the quarks. Take the UD quark. This should be regarded as wave functions. So it's a 2-column vector, and you transform it by an SU2 transformation to U prime D prime, which is just the UD multiplied by a unitary matrix called U. 2 into 2 unitary matrix. It's not only unitary but unimodular also. Unitary, you know, U dagger U equal to 1. Unimodular means determinant is 1, determinant of U. And the transformations, the group of matrices, I mean the set of matrices in 2 by 2 space which are unitary and unimodular form a group. They satisfy all the group postulate. So, under multiplication the set of 2 by 2 unitary unimodular matrices form a group which is called SU2. So, this U is unitary. This is called simple, not simple in the usual sense of the word. It's a technical word, means it is unimodular actually. Simple unitary transformation on 2 objects. Okay, I have defined it now. Yes, a good way of doing this U is writing this U is like this. Write it as an exponential of I. Now I will begin to make small letters, so let me be careful. Is it all right? Visible? This here this I is not this I, which is root of -1. This I is repeated. Anything which is repeated is summed over. I goes over 1, 2, 3. Summed over I equal to 1, 2, 3. You taus are 2 by 2 matrices. Actually, tau 1 is 0, 1, 1, 0. Tau 2 is 0 minus I 0. Tau 3 is equal to diagonal 1 minus 1, 0. I hope all of you can recognize this. These are the famous Pauli matrices which come when you talk about angular momentum theory or spin half. These are the 3 components of the spin vector. There it is called I think sigma 1, sigma 2, sigma 3, but here it is isospin, so I have changed the name to tau 1, tau 2, tau 3, that is all. So, multiply them by some real numbers, 3 real numbers, they are real number, and take exponential. I hope you know how to take an exponential of a matrix or even an operator. Exponential, use the exponential series. So, 1 plus this plus square of that plus cube of that and so on. Just go on expanding it, I mean exponential expansion use, and that is the definition of an exponential of a matrix. You can prove, since tau I are Hermitian and these are real, this property. So, that is a simple exercise. Prove any unitary unimodular matrix can be written like this. I can actually put another quantity exponential of I times theta 0 again a real number, an arbitrary phase, and that will also be unitary, but that will not have determinant 1. The determinant of 1 only removes that extra phase factor. Okay. And so, this is the most general 2 by 2 unitary unimodular matrix. So, we can use this. One important property of the Pauli matrix is, all of you will know, the commutator. I hope all of you know what is this epsilon symbol. Epsilon 1, 2, 3 is plus 1, epsilon 2, 1, 3, anything. If you make one interchange, it is minus 1. If 2 indices are identical, it is 0. Again, repeated indices k are summed over. The important property of Pauli matrices which are valid here also. Actually, now I want to write down in a little bit more generally. More generally, instead of tau by 2, I should write t. So, replace tau I by 2 by a general quantity called Ti, and these are called generators. These are 2 by 2, these may be higher dimensions. That is a more general way of defining SU2, but I defined it in terms of the fundamental representation. The isospin half representation, the doublet is the fundamental representation for SU2, triplet is the fundamental representation for SU3. So instead of that, we can go to the higher representations. I am going to talk about the higher representations. They are called generators. We do that. Actually, I think here I made a mistake. Please change it to 2 times I. But because of this 2, you will see that the commutation relations among the generators take the form same thing, except that 2 won't be there. I epsilon I j k, again repeated indices convention you have to follow. So these unitary transformations define Lie group, and these generators satisfy this algebra commutation relation. That is, any commutator closes under commutation. I mean, they close under commutation. That means the right hand side also will be some combination of T, and this is called Lie algebra. Actually, most of the time it is enough to use the Lie algebra. Okay, now I have defined everything possible for the group as well as representation, and the fundamental representation is this. Now let us go to other representations, the higher representations, which is what we need to classify the hadrons. I am still talking about SU2 only, I don't know. I thought I had SU3 also. Yeah, SU3 I will do later. Representations. What are the representations? Representations is what mathematicians call them, but we should, physicists call them multiplets. What we have been calling as multiplets, mathematicians call representation. So that the generators take up that dimension. So what are the representations? Spin half is doublet representation, and then triplet, then quadruplet, spin 3 by 2, and so on. So in our notation it is spin half, spin 1, isospin half, isospin 1. Remember, this mathematics is the same whether it is ordinary spin or isospin, although we are preferring to use it for isospin. And this is 3 by 2, and this is 2, and so on. These are the various representations. And I already mentioned this, let me mention once more. We can compose when there are 2 particles of spin half, isospin half, we can get them either 0 or 1. Another way of writing this is to say 2 into 2. Both notations we will use. It can be either a singlet. Singlet will be 1 here. This is 0 isospin, but number of components is only 1, and then there will be a triplet. So these are various ways of composing the representations, or composing the multiplets, or adding the angular momenta, or adding the isospins. These are various ways of thinking about it. So 2 is the fundamental representation. Of SU2, are also called the defining representation. The SU2 group itself has been defined using the fundamental representation. That is why the question came, where is 3 in SU3? Fundamental.
The form becomes small, sir.
Yeah, this is fundamental representation. Yeah. 2 is the fundamental representation, and let me illustrate this now. I already did it earlier. Alpha 1, now for a single objects, I3 equal to plus half, we denote by the state vector alpha. I3 go to minus half, we denote by beta. But there are two particles, I already wrote it down, but I mean no harm in writing it again. Alpha 1, first particle alpha, second particle beta, I am sorry, second particle alpha. Then we have the symmetric, these are all symmetric, alpha 1, beta 2 plus beta 1 alpha 2. I already did it, but just for completeness here, let me do it again. So these are the three members of the triplet, namely I equal to 1, with I3 being plus 1, I3, let's write down here, I3 here, plus 1 here, 0 here, minus 1. But all of them, the symmetry characteristic for the different multiplets have to be exactly the same. All of them are symmetric. Then if you make it antisymmetric, alpha 1 beta 2 minus beta 2 alpha 1. I am sorry, beta, first particle is always here, beta 1 alpha 2. Divided by 1 over root 2, that is the singlet, I equal to 0, which is antisymmetric. Okay. I think I have time to prove this now, because we have come up to the point where we can prove that. That is, how do antiparticles transform? That is the question we are asking. How do antiparticles transform under isospin? Antiparticles transform under SO2, that is the question. The answer is very simple. Let us again take a doublet like UD. Consider for antiparticles generally complex conjugation comes. I mean that I cannot prove here, only in quantum field theory it can be proved. The particle antiparticle relationship is by complex conjugation. So psi star will be U star D star. Then I make one more transformation. I multiply by I tau 2 you take from here. I tau 2 will be 0, 1, minus 1, 0 into U star I tau 2 psi star, is right. What is that? That because of that minus 1 which is coming there, this is basically it flips the up and lower components, which we know for antiparticles. I said that I3 gets changed to minus, so there has to be a flip. In addition, there is a minus 1. Both those are achieved by this I tau 2. So I tau 2 psi star is equal to n d bar d star I have written over here. Antiparticles normally are written as bar. So although I will, for wave function I will use star, so let us put u bar d bar. It's the same, you can either put star or bar, matter of definition. So this first of all flips between the up and lower component and then puts a relative minus sign. Now what we have to prove? We have to prove that if psi transforms as a doublet under isospin, transform as a doublet means what? This is the definition of a doublet. If it transforms by a unitary unimodular matrix, then it is called an isodoublet. Psi star itself will not do it, but I tau 2 psi star does it. That is what we have to prove. So for that purpose, I have to look at the U matrix, exponential of I. Let me use a notation, tau dot theta vector. This is a vector in isospin space, so it has three components, tau 1 theta 1 plus tau 2 theta 2 plus tau 2 theta 3. This is our U matrix. Now, please do this as an exercise. Show that this is cos theta by 2, I think, I tau dot theta unit vector sin theta by 2. Now, this theta, so I am defining theta as square root of theta 1 square, just like we do for ordinary vector. And this unit vector is theta vector. Theta vector, remember, has 3 components, theta 1, theta 2, theta 3, and then divide by this theta magnitude. Then it is called unit vector. Please prove this. It's a very simple proof because this is an exponential series, and remember the important property that all tau squares, tau 1 squared is 1, tau 2 squared is 1, tau 3 squared is 1. And you, because of that, you will be able to separate the whole exponential series into one part which does not have any, since tau squared is 1, all the even powers will join together to give you this cos theta by 2. All the odd powers will join together to give you theta sin theta by 2 with a multiplicative tau. So, actually in 2 by 2 unitary space, every function of tau is only at most a linear function. Tau square, tau cubed will be converted into tau, tau power 4 will be converted into unity, and so on. That is why this happens. So, please first prove this exercise. This is an exercise, very simple exercise, and using that so we know that psi transforms as a isospin, or I mean doublet under SU2, which means psi prime is this. Psi prime, psi transforms like this under SU2. That is what I have written there. The same thing I have written here in a different notation. So, take psi prime star first, which will be e power I tau star divided by 2 dotted with theta psi star multiply by tau 2. This is the important step. Multiply just by, because this is a matrix and it is a column vector, you can always multiply from the left by another 2 by 2 matrix, square matrix. So, that will be first from this V note. So, let me first write that, multiply this by tau 2, this equation by tau 2. So, you get okay, I simply multiplied on the left, then multiply this also by tau 2 psi prime. Maybe it can be done more simply, I do not know, I am doing it in a very clumsy way, I think. Tau 2 e power I psi star. The important thing is I have to commute this with this. When I commute this, what happens is e power, this becomes I tau dot. Remember, the signs are very important now. So, this is the important equation. How do I get this? You can see that this will have tau 1, tau 2, tau 3. Use this equation, not this form, but use this form. Tau 1 and tau 3 will, remember this equation, I do not know whether I wrote it right, yeah. When you try to commute this tau 2 with this, there will be a tau 2 here, and that will not change anything because tau 2 into tau 2 is again in the reverse order tau 2 and tau 1. Whereas the different taus anti-commute. Oh, that is again another thing I forgot to mention. There is an important property for this taus which is not valid for general generators. Anti-commutator now is 0. Tau 1 into tau 2 is the same as minus tau 2 into tau 1. That is what I was missing here. I was wondering why I am not getting it. So, first of all, write this in terms of this. Okay? When you write it, tau 1, tau 2, tau 3, all of them will come, and tau 1, tau 2 will anti-commute, so a minus sign will produce. Similarly, tau 3 and tau 2, but when it is tau 2, of course, there is no change, so no change is occurring, and so you can see that you can reproduce this now. You understand? See, tau 2 behaves separately from tau 1, tau 2 because tau 2 has a I, so tau 2 star is equal to minus of tau 2. So, minus comes that way, whereas tau 1 and tau 3 anti-commute, so minus sign comes. So, all this minus becomes plus. So, this is plus. So, what have we proved? The tau 2 psi prime star, tau 2 psi transforms exactly like the original psi. That is what I have proved. So, it is tau 2 psi prime star which has to be used for denoting antiparticles. That is what I said here. This d bar u bar E is nothing but so this is equal to I tau 2 u d both star. Here we are writing simply minus bar. So, take flip them, but then multiply by, you have to multiply by I tau 2, and what is I tau 2? I tau 2 gives you this relative minus sign. It flips like this and then gives a minus sign. So, I have proved that if ud transforms like an isodoublet, then once you take complex conjugate, you have to multiply by I is unimportant. I am multiplying by I so that this gets converted into 0, 1, 1, 0. 0, 1, minus 1, 0. It is this minus 1 which is crucial. I into I will give you a minus 1. So, that is all the proof of this. So, we know how to transform the antiparticles. I mean, how to get the correct I equal to half object from antiparticles like antiproton, antineutron, or anti-u bar, anti-u or anti-d. I think I should stop here. So, now I am going to go to SU3 that I will do next week. So, I think I will stop here. I have already exceeded my time by about 5 minutes. Okay, but there are questions another 5 or 10 minutes. Yeah.
One person asking.
Yeah.
Why you did not write spatial wave functions for neutron, proton, sigma, etc., but wrote it for delta?
Now, I took an example because from there only I can easily prove that a color quantum number is needed. Once I prove it, it is valid for all of them. Because remember, all those other wave functions also are completely symmetric now without color. I mentioned, I forgot, that Young's table, symmetric Young's table, all the 3 in the horizontal row is valid for all the hadrons, proton, neutron, I mean all the hadrons in the decimate. It is a decimate which is useful for this, because in the decimate the SU3 wave function is completely symmetric. Remember, I wrote completely symmetric. Look at the composite quark wave functions I wrote for the B star. You will see not only for delta plus plus, but for all of them it is symmetric. But it is easy to guess that it is symmetric because delta plus plus is symmetric. And then the spin wave function, of course, I am taking all the 3 spins aligned together, it is symmetric, and these are supposed to be ground states, so spatial wave function is symmetric. So, all this argument is valid for all the 10 particles. Although I used delta plus plus, I could have used it for the omega minus, I could have used it for the delta minus, either UUU, DDD or SSS. In these three things it is simpler. Otherwise, otherwise also, in fact, I have already written down the symmetric wave function. So whatever I have said is valid for all the 10. The symmetric properties have to be the same for all the members of a multiplet of an SU2 or SU3. Okay?
Okay, sir. Thank you, sir. Okay, no more questions.
Okay. So we will meet again next week, exactly at the same time. Yeah.
One question.
Yeah.
This 2 cross 2
Yeah.
is equal to 1 plus 3.
Yeah.
This we are familiar in the angular momentum.
Correct. Correct.
So this kind of representation
Yeah.
of 1 dimension and 3 dimension
Yeah.
is because of the vector nature of the angular momentum.
Correct. Correct. When you add a spin half and spin half, the total angular momentum has to be either 0 or 1. That is proved. That is proved just from the commutation relations. That is the only important thing which you learn in quantum mechanics.
Yeah. But now I am asking, if I mathematically look at a 4-dimensional vector space,
yeah,
I could have written it as a direct sum of 2-dimensional vector spaces also.
yeah, but they are not irreducible representations. The 4-dimensional vector space now separates into two the idea of irreducible representations. One, a single dimension, another 3.
Yeah, that is in angular momentum.
But the same thing is valid, because the mathematics of angular momentum is valid for this isospin SU2 also. There is no difference.
I am asking, is there any other quantum number with respect to which we can say 2 cross 2 equal to 2 plus 2?
See, all you have to do is to use, see, in angular momentum theory, the generators there are simply angular momenta, so let me call them J. From this basic commutation relation of angular momentum theory, by the way, the anti-commutator relation is not valid for any other thing except their doublet. So only for Pauli matrices they are valid, not for spin 1 matrices or spin 3/2 matrices. Similarly for angular momentum. So from this we can prove that when you multiply two representations, they become they separate into two irreducible representations, one dimensional one and another 3-dimensional. There is nothing else possible.
Yeah,
that is what we prove in angular momentum theory.
Yeah, that is true. But I am asking, is there any other algebra which I can think of where 2 cross 2 can be written as 2 plus 2?
I don't know what algebra that will be. It is certainly not the Lie algebra of SU2. Whether 4 separates into a doublet representation and another doublet representation. I mean, you can certainly do it mathematically, I suppose. Whether it will correspond to anything physically, I do not know. Even mathematically, whether consistently we can do it, I do not know. I don't know the answer to that.
For example, if you look at Dirac's force final representation.
Yeah.
So electron and positron.
Yeah.
Can we think of them as 2 plus 2 if we say?
No, but there it is different. See, you are talking about the 4 spinor, the Lorentz spinor, right? The Dirac spinor. Dirac spinor has a 4-component object, and there we have to use the Lorentz group. When you use the Lorentz group, I do not know, but Lorentz group has the subgroup ordinary spin group also, rotation group also. So the same, as far as spin is concerned, the same property of 1 component and 3 component will happen. But you see, actually that is more subtle, because although you write down as a 4-component object, thinking that it is 2 spin up and spin down electron and spin up and spin down positron, you know that that is not quite correct. The 2 spin up, actually what you should say is electron with positive energy spin up and spin down, and electron with the negative energy spin up and spin down. These are the 4 components of the Dirac spinor. And in order to get positron, you have to go to this process of filling all the negative energy levels, and it is the absence of that which is positron. Although the 2 extra components correspond to positron, it is not as simple as that. You cannot identify. Yeah, it is more subtle. You have to fill up the whole negative energy C, and only the hole in that is antiparticle positron. I think if you take the electron spin up and spin down and positron spin up and spin down, it will not have a well-defined Lorentz transformation property. It will not be a Dirac spinor at all. Yeah. Yeah. Yeah, we will stop here now and we will meet next week. Okay? Thank you.